Hello, my name is Julian Osorio, and I'll be doing the STK project for a small satellite. So first, we're going to start with clicking the satellite, double click it. We'll change this to the 1U CubeSat, which was required of us. Inclination angle is 55, altitude is 450, and then apply. Okay, close. We'll set these to tile vertically. This is the 2D ground track, first part that we have to show. This is the 3D model. So if we go to this first satellite, we'll change this to HPOP, and then we will click apply. Wait for it to load. And next we have to plot the semi-major axis length, eccentricity, and inclination angle. This is fine. We'll just click OK. OK. So we'll go to Report and Graph Manager. If we keep this open, you'll see I have set up already what we need to find, but we'll specify time properties. Looks good there, and then we'll just click the semi-major axis line. Yes. You can see as time goes on, the semi-major axis line decreases due to the lifetime of the satellite. Next, we'll go to the eccentricity. And because it's a circular orbit, it's pretty much going to be very close to zero the whole time as it orbits the Earth. And then we will do the inclination angle. And you can see it's fluctuating as time goes on. We'll close that. We'll click close here for now. And then get the lifetime of the satellite. We'll right click, hover over satellite, click lifetime. We'll change this to 2.5. We'll change this to centimeters squared, make that 100 centimeters squared. Make this the same, 100 centimeters squared. And then this was 1.2 in the assignment. We'll change the first density model to the 1976 standard compute. May get here about 1.4 years. Okay. Next one, we'll use the Jackie Roberts compute, 1.1 years. And then we'll use Jackie 1970, see what happens, 1.2 years. Close. And then now we have to find the coverage area. So we'll go insert new sensor, click the satellite. Okay. Close. Double click the sensor. Change this to 55, which was asked for. Apply. Okay. Right click the sensor, report and graph manager, and then we'll click footprint area. We can just change this to copy. Paste, and then we'll make this what? December 12th. And then footprint area. And yeah, you can see here, this is about the area that I got for my theoretical value. Pretty close to it. So it looks good. Um, then we have to show the beta variation. So if we close this, well, we can delete the satellite because we're done with it. Yeah, the sensor, I meant. Next, we open the satellite again, report and graph manager, and then we'll plot the beta variation, which you could see is already set up. Okay. This is the beta variation as the satellite orbits the Earth. You can see here at 0, this is the maximum eclipse angle, and this will be the minimum eclipse duration, which this is the minimum beta angle, which would be the max eclipse duration around December 23rd, and then the minimum eclipse duration will be around April 17th. Next, we need to show the umbra penumbra. We'll click eclipse here for about the same time period. You can see it's a little hard to read. But this is the umbra penumbra and sunlight time. We'll close that. I'll change this to 5 days to make it a little bit more readable. We'll change it again to December 12th, and then uh, and then click it in again. You can see it's a little bit more visible. See what's actually happening. Maybe if we change it to a day, to like 2 days, see what happens. Yeah, you can see it's a little more clear to see what's going on. Close that. And then we have to determine the maximum eclipse duration, which is pretty simple. There we go. Using the beta variation at a specific, here we go. If we go to the beta variation again, the change in the beta angle. If we use this minimum and maximum beta angles at the specific days, and if we find the days, we can use the eclipse duration to find the minimum and when they happen. Was that? And then lastly was to perform a Hohmann change and a Hohmann plane change combined, which I can show you right now. We open the satellite, we'll change this to astrogator, change this to Keplerian, we'll change our height to our desired height, 6282 kilometers, eccentricity 0, inclination 55 degrees. We'll change this propagate to propagate 2 hours, and then change this to hours, and then make this 2 hours. Next, we will create a target sequence and name it begin open. Next, we'll insert a maneuver, call it DV1. Make this a thrust vector, select the X, and then go down here to results. And then we will click coupling elements and then radius of apoapsis is OK. Click here, differential corrector, select, we'll change this to 11878, which is our desired outcome. Convergence is 50 iterations. Go down here, we will we'll create another propagate, move it outside. I'll name this 2FOG. And then this will be an apoapsis. So click this, click that, delete the duration. And then go back down here, create a target sequence, and then name this finish Hohmann. And then we'll go here, make a maneuver, name this one DV2. Next, we'll thrust vector, make sure only this X one is selected for both of these. Results, and I believe this one is a eccentricity. So Keplerian eccentricity. Okay, if we go back to here, and then select both. Because we want a circular orbit, we'll keep the eccentricity to 0. Okay, and then we go down here and click insert another propagate. And then we'll name this to ascending node. Click that. We'll change this to ascending node. Delete the duration. And then change this repeat count to 2. Next, we'll go down here, make another target sequence, and then name this simple plane change. Go down here, new maneuver, DV3. Make this a thrust vector. Make sure both of these targets are selected. Go down here to results, Keplerian, and then inclination and eccentricity. Okay, I'll go back up here, select properties, make sure all of these are selected. And looks good. Convergence still 50. Okay. And then lastly, we will come down here and then make another propagate and then call this 36 hours. Next, we'll change this to hours and then 36, like we said. Should be ready to run now. Applied, everything looks good. And then run. Well, first we make sure these are running active profiles. Active profiles and then run. So now with the now is that it was able to converge. We'll see. Here we go. Converged. We can see the run plan here once we click play. You can see the satellite going around, going around and making its way through a Hohmann transfer, then a simple plane change. What we can actually do now is copy this, paste it to keep it around the same. We'll uncheck this, and then we'll open satellite 2. What we can do here is delete this, move the ascending node up, delete the finish Hohmann, and then ensure that everything else stayed the same. So altitude, inclination angle, ascending node is still the same. It's good. Begin Hohmann, radius of Epwest is okay. DV1 looks fine still. To apogee, everything looks Epwest looks good. Differential corrector, check everything, make sure everything is 0. Okay. DV3 still looks fine. And then the propagate 36 hours. For some reason, it doesn't work. It won't converge. Let me show you. First try. But if we add, what was it? Apoasis, delete the duration, I run it again. And then we do the same thing, but we put the duration back. Close this, change the duration back to hours, 36 hours, and then apply. And then if we run it, it should converge. There we go. It converged after we reset the duration. Okay, and then you can see the the combined Hohmann and simple plane change for both. You can see it did it without the extra maneuver. If we click reset, we can actually, if we go to report and graph manager, If we select both satellites and then we click down here to a maneuver summary, open this, you can see how much delta V is required from the both separately and then combined. So as you can see, this is 7,000 delta V compared to 6,000 delta V here, which is a lot of saved delta V, which becomes a lot of saved fuel and a lot of saved mass. I believe that is all that we need to do for this STK project. Thank you for watching.